Hi everyone, welcome to our tutorial on responsible data integration, next generation challenges. Fatima Nagasian from University of Rochester and I, Abul Asude, are going to present the tutorial today. This tutorial is in collaboration with HV Jagadish from the University of Michigan. Okay, AI needs data, right? So nowadays we hear about data-centric AI a lot. But like data is the foundation, right? So the question is, how is the data collected? Data is usually obtained through multiple sources, and usually very little is known about how the data is generated and collected, and what the process of data cleaning and integration has been. On the other hand, the entire pipeline of data, in particular data cleaning and integration, have a significant impact on the outcome of the models. All right, so here we have a responsible data pipeline that is taken from a recently accepted paper in ECM computing surveys. And here, when we look at the pipeline of the responsible data, one can observe two main products of the pipeline being the data and the algorithms. And just quickly, if you look at it, you can see that almost all of the work for the fair ML community and in general algorithmic fairness community has been on the second product, being model or algorithm, trying to make sure that fairness in the outcome of the algorithms has been satisfied, and usually they have some processes for pre-process intervention, in-process intervention, and post-process intervention. The focus of this tutorial, though, is on the first product of the data pipeline, being the data set itself. So now, just as fairness makes sense for algorithmic outcomes, bias makes sense for data. We'll get to that. And the pipeline of the data to generate the data set is the fairness-aware data preparation approaches that we will touch on some of those approaches with a focus on data integration. Okay, so to get to the outline of the tutorial, we're going to have the tutorial in 4 parts mainly. In the first part, we're going to talk about the next generation requirements of the responsible AI. Then we will revisit data integration, and we will talk about fairness over data integration. And finally, we will have some open problems. So let me begin the part 1, being next generation requirements of data. And as I just earlier mentioned, data is one of the most important components of AI systems, and we all know that garbage in, garbage out, right? So if the data that has been provided for AI models is not good enough, you cannot expect good outcomes, right? So therefore, the first step to achieve responsible AI is responsible data. And right, and it definitely includes data integration. Okay, so in the rest of part 1, we'll review some of the requirements for the data through the lens of responsibility. Right? Okay, that's what I'm going to do. The first requirement is that the data that is going to be used for generating AI models should be an IID random sample drawn from the distribution that query point follows. Right? Okay, so this is a fundamental requirement of machine learning, not specifically to responsible AI, but when we are talking about responsible AI, it becomes even more important. It sounds easy, like IID random samples, it's always the assumption, but it's not easy to satisfy. And more importantly, it's not easy to verify. And let me just elaborate on that with a few examples. So for those of you who cannot recognize it, this is screenshots of city of Chicago, the map of city of Chicago. And you can see that, for example, the top figure shows the distribution of demographic groups. The bottom one is the distribution of like different incomes, jobs, or degrees across the city. And it's pretty easy to see that distributions for different demographic groups are different. And it's usually the case for social data. And in particular for the city of Chicago, the reason is an unfortunate historical bias that is called redlining. If you are interested, you can just check redlining to see like how historically racist policy can leave its impact on the society and therefore on the data centuries after. Right? So, nevertheless, so we see that the data is not well distributed. So now, if you collect the data from certain parts of the city, right? If you collect the data from the center, certain parts of the city, you're not going to satisfy the IID sample requirement. And keep in mind that you cannot just randomly select sample points from this map because the densities of different regions are different, right? For example, close to the mid-center east of this map, the population is far more than the left side or west, right? So, all right. So, I guess hopefully it makes it clear that why it is not clear to sample in an IRD manner. But even if you can select samples randomly, right, which means that you don't have a selection, right? You randomly select the samples that you want to collect. Still, you can bias can be introduced. To see an example, consider these two examples that you want to collect a survey, and the question in the survey is that do you like responding to surveys or not? And there are two options: yes, I love responding, and the other one is no. And obviously, after collecting the data, you're going to see that near 100% of the answers are yes, I love responding to surveys, but it doesn't mean that like people like responding to surveys. Right? So here, what we have here is called sampling bias, or more specifically, a self-selection bias is happening because some people opting to answer to their surveys, the other do not. Right? So, So even if you don't introduce selection bias, you may still have sampling bias. And finally, after all of this, it's not easy to verify that the data that has been collected is unbiased or no. The reason is that usually the underlying distributions are unknown, right? So you know little about the underlying distribution, and therefore it's very challenging to verify that if the collected data is an IRD sample of the underlying distribution. Okay. So the next requirement of responsible data is called group representation, and that means we need a representation or adequate representation of different demographic groups, or in general different groups in the data, right? So if the data is only collected from the white people, that's not what we're looking for, right? So we want a good representation of white, black, Hispanic, male, female, etc. Right? So we want the data to be the representative of all. Okay, next question. What happens if the data does not satisfy group representation? And let me explain it with an interesting example. Early detection of breast cancer is very important. Breast cancer is a big issue. In particular, in the United States, breast cancer is a big issue. It's one of the major causes of death, unfortunately, among the females. And therefore, creating tools for early detection of breast cancer is super important. Right? So now let's say that you want to create such a tool, and you are using breast cancer data. Right? You have a data set of breast cancer that's given to you. Right? So you have that data set. You want to create that tool. So do just partition the data into train validation test, train the model, and then test it using the same split of that dataset. You see that, okay, it satisfies the test set, the test accuracy is high or S1 is high, and therefore you conclude that, okay, I have a good tool for prediction. And note that this data has been taken uniformly at random from the same distribution that the training data has, right? That's why it makes sense that your test accuracy should be high. Now let's say that your data set doesn't have enough black females, which is pretty normal and usual, and it is a big issue in breast cancer data. But in particular, in the city of Chicago, we have a big problem collecting black females breast cancer data for many reasons that I'm going to skip now. Okay, now if you use this early detection tool that you have for breast cancer on black females and make a prediction, two cases can happen. Case one is you are lucky and the behavior of black female and other demographic groups, especially white, is the same, and therefore your tool is going to predict them well. But if you are unlucky and the behavior of breast cancer on black and white females is different, then your model is not going to have a good performance for tools, which unfortunately is the case. So the behavior, the breast cancer behavior for black female and white females is different, and therefore we see this disparity in the behavior of the model. So how can we resolve this issue? To resolve this issue, we need to make sure that we have good representation from all demographic groups, including black females, right? So that's why when you are looking at responsible AI and responsible data in particular, group representation requirement is very important. How is the group representation is measured? There are two well-known measures or metrics. One is representation ratio. It requires almost equal representation from different groups. And the other one is the data coverage, which is a more liberal metric that requires enough. What is enough? I will get to that. Representation of different groups. I'll get back to group representation and data coverage if we have time, hopefully. All right, the third requirement. So far we talked about data should be already samples. Data should be representative of different demographic groups. And the third one is that the features, so now we're not talking about the tuples or sample points in the data, we are talking about the features that has been collected, right, or reported. Those features should be both informative and unbiased. And I'll get to that. What do I mean by informative and unbiased? But first, let's set some ground. We assume that the data set is a collection of features, x1 to xn, usually known as the observation. And we may have one or more target variables, also known as labels. And the data, when we are talking about social data, also involves sensitive attributes, at least one sensitive attribute, such as race and gender. And all right. So what is critical about sensitive attributes is that you may or may not have the sensitive attributes, right? So the data that has been collected may not contain the sensitive attributes. This makes the situation very challenging. And to give you one example, just consider a website, right? And the customers of the website. The customers of the websites, they may not even subscribe, right? Or even when they subscribe, I mean, it's very strange if the website is collecting their race, right? So they usually don't do that. I mean, they almost never do that, right? They don't collect the racial information. So now you have data that contains the observations, but it doesn't have the sensitive attributes. So that's a dilemma. How can you audit fairness when you don't have access to the sensitive attributes? One resolution is that you could use proxy attributes. What is a proxy attribute? A proxy attribute is an attribute that has a high correlation with the demographic information and therefore can kind of like reveal for us the demographic information. For example, from the name, you can guess the gender, right? So you can guess like if it's a male or female. But that is problematic. What is the problem? The problem is that for different demographic groups, you may or may not accurately guess the groups. For example, some names are gender neutral, right? So for those, you cannot guess the gender very well, and that can lead to some group unfairness. Okay, so what do I mean by informative feature? Obviously, you're using features as observations to make some predictions, right? If we're considering predictive tools, right? So you're using these attributes or features as observations for prediction, and therefore the observation should highly correlate with the target variable, and more correctly, the target variable should be guessable or predictable from the observations, right? So it means that it should contain enough information that by looking at the observation, you can guess what the variable is, all right? So the features should be informative. At the same time, the features should have a very low correlation with the sensitive attributes. Because if your sensitive attributes, let's say gender, and your observations, let's say salary, are highly correlated, then in these situations, the models that later on are going to use this data might become unfair, right? So if you want to make sure fairness down the road in the pipeline of the data, you want to make sure that the features you collect are unbiased, right? So now I talked about correlation. Correlation has been a little bit sloppy by using the word correlation. More accurately, I mean that the sensitive attribute should not be predictable from the observations, right? So it means that there is little to no information in the observations for the demographic information. And ideally, we want X to be independent from the X. Right, to summarize, we want the features that have a high correlation with the target variable, and at the same time have a low correlation with the sensitive. And finally, we want the correctness and completeness always has been an important feature for the data, right? We don't want missing attributes or incorrect values in the data, right? But it becomes even more important when you are talking about responsible AI, because such cases can cause to an increased an increased bias in the data. Let me give you an example. So consider a case that there are two demographic groups, for example, minority and majority, and a small portion of the data belongs to the minority and a large portion belongs to the majority. Now consider a simple task, and that simple task is to compute the average, right? Now, if you have an incorrect value for the majority, that incorrect value is not going to significantly change the average for the majority, right? But on the other hand, if you have an incorrect value for the minority, given that you have a few of the minority samples, that can significantly skew the value of the average. Okay? Similarly, if you have missing values, that missing value, you need to have a resolution strategy, right? For example, you can remove the rows that have missing values. Now, if you remove a row that belongs to that have missing values, and that row belongs to the majority, almost no harms to the majority will happen because you have many samples from the majority, right? On the other hand, if that happens for a minority and you remove the row for the minority, you already have a few samples for that group, you're going to have even less. Another example is if your strategy is to replace the value of the empty values with the average. Let's say your imputation strategy is column average. In that case, the average we know is driven by the majority simply because they are the majority, right? So most of the points are from the majority. So in that case, you are even increasing the bias in the data. replace the values for the average. So therefore, correctness and completeness in the data, though important in general, is even more important for responsibility. Last but not least, scope of use augmentation is very important for responsible data. So far, we talked about 4 features, right? Or sorry, 4 requirements, right? And but key part is that most of the times it's not possible to satisfy all requirements, and some of the requirements can even have conflict with each other. For example, IID sample requirement with group representation requirement can have some conflict. So you cannot at the same time fully satisfy IID sample requirement and group representation. Right? Therefore, you may not be able to collect the data that is good from every aspect. And as a result, it's very important that for data at hand, we should augment the data with the scope of use, right? That specifies like what are the boundaries of use for this data, and to ensure transparency, one need to embed data with metadata and information that describe its collection process, limitation, fitness for use, and it should include information about the underlying distribution, existing biases, both from the group representation and also biased features, and also you should have the information about correctness and completeness in data. Okay, so with that, I talked about 5 requirements. In the rest of part 1, I'm going to zoom into one of these, and that's the representation bias in data. Before starting my part on representation bias in data, I would wanted to give a shout out to my student Nima, who did a great job for putting together the survey that I used for the rest of the talk, and he couldn't come, unfortunately, here due to the visa issues. All right, so representation bias. Representation bias happens when data underrepresents and therefore subsequently fails to generalize for some parts of the target population, right? So that in general is called representation bias. And representation bias is not a new problem. It has been studied and known in the data mining and database management communities and also statistic communities. And there are some works from late 90s or early 2000s related to it. But our focus in our talk is on representation bias through the lens of responsible data science, which is a recent line of work that appeared after 2017. Representation bias in data can happen for many reasons. One of them is historical bias. Historical bias, we saw the example for the city of Chicago. We saw that we had the representation bias, that some parts of the city had basically more representation of some groups, and the other groups not very well represented there. And right, so historical bias should be blamed for that. Sometimes there is underlying distribution skew, which means that some demographic distributions are naturally smaller than the other ones. For example, in the United States, we have a population of, if I'm not mistaken, 13 to 17% of Black, and somewhere around 65 to 70% of white. So there is an underlying distribution skew, right? And that can cause representation bias. And also biases in sampling, selection, and self-selection, as I just explained it through the survey example, those can also cause representation. Okay, so measuring representation bias, there are 2, as I earlier just glanced through it, there are 2 well-known measures for measuring representation bias. One is representation rate, that is also known as base rate or prior probability. And it requires that the data should have an equal number of objects from different groups or subgroups in the data set. In other words, the probability of every group within the data should be the same, right? And then if you have a requirement tau, you want the ratio of number of one population to the other one to be larger than tau. The one is the perfect situation, and here we assume that the minority is at the denominator, so it's a value smaller than one. We want it to be as close to one as possible. Okay, so considering the fact that underlying distribution can have a trade-off with the demographic groups. In other words, like different groups may have different representation in data based on the underlying distribution skew. It is not easy to satisfy representation rate and the underlying distribution at the same time. Therefore, coverage is a more liberal measure that instead of having equal numbers of objects from different groups, it requires enough numbers from those groups, right? So saying that, for example, if I have K samples from this demographic group, like if I have, let's say, 100 females in my data set, I'm good, right? So it's not concerned about the ratio, it's concerned about a number, an absolute value. Okay? So, in the survey, several taxonomies for representation bias literature have been provided. Representation bias has been studied within different communities and within different types of data, structured data, textual data, image data, graph data, etc., etc. This is a taxonomy for the structured data. For more information, I recommend you to. So when we are talking about representation bias, in general, at a high level, we can talk about how to identify representation bias in data, and second, how to resolve representation bias in data. Now, for the identification, there are two categories when the attributes are discrete or categorical, non-ordinal categorical, or when the attributes are continuous. And in order to resolve representation bias, two cases can happen. Either you have the option to add more data points, or you don't have the option to add more data points. If you have the option, I mean, the line of work for adding more data contains different works. This tutorial is centered around data integration, and we're going to have a deep dive on data integration. In other words, how to use data integration for responsible AI, and one of those aspects is going to be representation bias. And if collecting more data is not an option, then the alternatives are generating proper signals or data labels and data sheets and query writing. In the rest of this part of the tutorial, I'm going to focus on the two blue lines. So that is identifying representation bias on continuous attributes and discrete attributes on a single data set. In this tutorial, we touch upon the orange rectangles, which is integration, data labels, and query rewriting. We may also talk about the proper signal generation, depending on if time allows. Okay, so let me begin with the very left branch of the taxonomy, which is coverage on non-ordinal categorical data. In this situation, the attributes on which you want to satisfy proper representation of different groups, those attributes are categories. Okay, so data structure that has been introduced for studying coverage in these cases is called pattern. And a pattern is simply a string that every value in it is an X, which means it's not identified, or a value. And just to explain it in simple terms, let's consider this pattern x2, x0. This stands for all tuples for which a2 is equal to 0 and a4 is equal to, a2 is equal to 2 and a4 is equal to 0, right? And note that a1 and a3 is not identical. And on top of the pattern, on top of the patterns, a relation, a parent-child relation is defined as pattern is the parent of another pattern if it only differs in one cell and that if in one of those is not identified, but the other one is identified. For example, x2xx is a parent of x2x0. And note that all the tuples that match x2xx also match x2x0. What is the goal? The goal is to find the uncovered patterns. What is an uncovered pattern? A pattern for which there are less than a threshold of samples in the data set that match it. And in general, and more specifically, we are interested to find maximal uncovered patterns, and those are the patterns that, first of all, those are uncovered, and second of all of their parents are covered. Okay, so let me just explain everything through this example. Suppose that we have a data set at hand, which is the toy data set, which is the one on the top right of the slides. And the graph at the bottom, every node of it is a pattern. And we can see that the parent-child relationship between the patterns is specified as the edges. Now, let's see what are the uncovered patterns and also the maximal uncovered patterns in this. So, obviously, 1, 0, 1 is an uncovered pattern because we don't have any sample in this data set that match 1, 0. Right? And let's suppose that the coverage threshold is equal to that. But its parent, one of its parents, x1 is also uncovered. Therefore, even though 1, 0, 1 is an uncovered pattern, it's not a maximum. And then our job is to identify the ones that just the topmost uncovered patterns. And in this case, it's 1x. And what does it say? It says that in this data set, there is no tuple for which A1 is equal to 1, independent of A2 and A3. Right? It doesn't have anything for which A1 is equal to 1. Okay. How to efficiently specify the uncovered maximal uncovered patterns? We have there are different ways of doing it. You can do it top down. You can go through this graph top down or bottom up. Both of these strategies have disadvantages, and one is just to smartly explore this graph and just prove parts that are not, that are provable. In the interest of time, I'm not going to go to the details of the deep diver algorithm. I encourage the curious readers to refer to it. Okay, so from the experiments, I'm going to only show one result, and that result is we are looking at the, I suppose it's a compass data set. In the compass data set, we created different cases with different coverage of the Hispanic females group, and we created a model that had overall accuracy of 76%, and we observed the accuracy for the demographic for Hispanic females across different cases. First observation is that when we don't have any coverage for the Hispanic females, the model is doing a bad job with those. So it has an accuracy of 47%, which is less than random, right? And the second observation is that as we add more tuples to the dataset from this specific group of Hispanic females, the model's performance increase, and around 80%, when we have around 80 Hispanic females in the dataset, it gets to an okay accuracy of near 70%. In summary, coverage enhancement. Okay. So before I go to the coverage over continuous attributes, I wanted to quickly show our system mixture coverage, which is for generating MOPs, maximal uncovered patterns in the dataset. In the system, as you can see, in part A, you can specify first a dataset, and then you can specify your attributes of interest, and then the level up to which you are interested in seeing the uncovered patterns. And then when you do the generate, it gives you this tree. And to interpret this tree, you have to start from the leaf nodes, and the path to the root shows the uncovered patterns. For example, the very top one is saying this data set doesn't have enough individuals from race Asian. So for example, this one is saying that it doesn't have enough Hispanics of the age between 35 to 60. Okay, so that first identifies the uncovered regions of the data, and then you can also try to resolve it. Right? So, for example, I did talk about coverage enhancement, but it also gives you some options on what are the options on how to improve coverage in this data set, which I'm going to skip. So the last part of the representation bias that I'm going to cover is data coverage over continuous attributes. We say a query point is covered by the training data if we have enough similar samples in the data to the query. Formally speaking, coverage is true if the size of the neighbors of the query point is larger than k, or it's at least k, otherwise we say it's not covered. And for similarity in this work, L2 norm has been used. And then the uncovered regions is simply the universe of all uncovered query points, right? Possible uncovered query points. And the goal then is given a data set and the attributes, we want to find this uncovered region. I'm going to go over the 2D case because it's geometrically interesting. So I think it's nice to at least take a look at the simpler 2D case and see how we can identify the uncovered region. Let's take a look at this example. In this example, we have 100 points in the 2D plane. And let's say that the coverage threshold is equal to 2, and the neighborhood is identified by a distance of 0.1. So we say 2 points are similar to each other if their distance is less than 0.1. And then we say a point is covered if it has at least 2 neighbors in the tree. So, I mean, if we identify if we somehow magically identify the uncovered region, the red dots in this figure shows the uncovered region. But the question is how we are going to identify it. To identify those regions, we make an interesting connection to the concept of Warnite diagrams. For those of you who are not familiar with Warnite diagrams, Warnite diagrams are geometric indices that partition a 2D plane, in general a D-dimensional plane, but now we're talking about 2D, right? They partition the plane of endpoints into a few cells, such that all the points within each cell have the same nearest neighbor. Right? For example, if we, I'm not sure if you can see my cursor. Okay, so for example, if we look at this region, for every query point in this region, the nearest neighbor is this block. Okay. And then how to generate Warner diagrams is a very good stuff. And K-Warner diagram is an extension of the Warner diagrams to, instead of looking at the nearest neighbor, we are looking at the K nearest neighbors. And here we have the two Warner diagram of the same point set. And for instance, if you look at this specific cell, for this cell, this point and this point are the nearest neighbors. As I said, K-Warner diagrams and Warner diagrams has been very well studied in the literature by the geometry community. And we know that the K-Warner diagram contains in the order of K times n minus K cells. And the construction of the K-Warner diagram can be done in the time of order of K squared and the log n. And after that, figuring out if the query point is covered or not is going to only take log of an order. So, but what is the connection between the K-Warner diagram and what we are doing here? Well, recall that our objective is to find the uncovered region. How are these two connected? And to see the answer, let us consider this region, the region very highlighted here. Note that in this region, the two nearest neighbors are the ones that I'm showing, right? This point and this point are the two nearest neighbors. Okay. So now, if we limit ourselves to only the points that fall inside this region, we know that all other points in the training data are further than these 2 points, right? So these two are the closest to every point within the set, right? For every point within the cell, the minimum distances are this and this, right? So what we can do is that we can simply eliminate all other data points for the entire cell and only consider these 2 points, right? What is the consequence? The consequence is that if we look at the circles with radius 0.1 centered with these 2 points, and the intersection of this with the cell we are interested in, everything that falls inside the intersection of the 2 circles is covered, right? Because for every point inside this region, the distance to the 2 nodes is less than 0.1. But every point that is outside, every point inside the cell, that is outside the intersection of the 2 circles, that is uncovered, right? Because the distance of that point, which at least one of the 2 nearest neighbors is more than 0.1. Okay? So then the rest is simple, right? For first construct the K-Warner diagram, then for every Warner cell, add the region outside the intersection of 2 circles to the uncovered region. Okay? And then to find out if a query point is covered or not, all you need to do is to identify the Warner cell that to which Q belongs and return uncovered if that point falls outside the intersection of the 2 circles for that cell, or in general the case. Extension to from 2D to MD. Yeah, theoretically, for a constant number of dimensions, you still can use Warner diagrams, but practically no due to the case of dimensionality. And then how to resolve the problem. We have a very interesting learning algorithm based on the concept of epsilon nets. We have a few theoretical negative results and some practically interesting algorithms, which I'm not going to explain in the interest of time, but I encourage you to take a look at the paper. Okay, so but let me conclude this part with a proof of concept example. Suppose that you have this toy example of where you have a cat, and you want to identify if a point on the plane, on the 2D plane, is inside the body of the cat or if it is outside the body of the cat, right? So it's a simple concept. Just specify a point, you tell me it's inside or it's outside. It's a simple binary classification. classification, right? Now, let's suppose that we don't have any points in the training set from this square here, which is this square is uncovered, right? And in other words, this part is removed from the figure, and all the training data has been collected from the rest of the image, right? So now if you create a classifier on this data, what we observe is that for the uncovered region, the classifier is not doing a good job. In fact, what we observed was that it simply is connecting this part to this part. It completely ignores the right ear of the cat. So therefore, we have a very high false negative that belongs to the ear of the cat. And yeah, so right. So we initially have pretty bad false negative, close to 0.4, and a low F1. But as the coverage increases, we see that the false negative rate quickly drops, and also F1 quickly increases. Okay, so right. Yep, with that, I want to conclude part 1. And do we have the break now, or are we going to?
I think we have 14 minutes left. Hi everyone, this is Fatima. I'm going to present the second part of the tutorial, which is revisiting data integration. In this part of the tutorial, we're going to revisit some of the data integration tasks and their connection to responsible data. We're going to go over a set of some of the existing work, old and new, and see how they can contribute to responsible data. And more specifically, we're looking at dataset discovery, data cleaning, random sampling over join, and data profiling. The first data integration task is dataset discovery. Dataset discovery is the task of identifying relevant datasets to a data science task at hand. It is normally formulated as a search problem given a query, the goal, and a data repository. The goal is to identify data sets in the data repository that are relevant based on some notion of relevance to the query. These data repository vary from open data lakes. These are open data sets published by governments, to enterprise data warehouses, which are very large, and also very recently to data markets. So there are all sorts of data repositories that we want to be able to search in them. Their size varies. For example, Singapore Open Data has over 11,000 data sets. And a single source, which is web table data, could have over 50 million data sets. So we're dealing with very, very large data repositories, and we want to be able to do search in these data repositories based on a query. So what's a query? The query could be a keyword query. And in this case, we're basically performing information retrieval style of search over metadata of data sets. And this is what Google's dataset search engine does. So it's basically web search algorithms over the metadata of data sets. So that's one way of performing dataset discovery when the query is a set of keywords. But the query could be also a dataset itself. It could be a table. And in this case, we would want to be able to search based on SQL operations, for example, join operations and union operations. And in this style of search, our focus is mostly on efficiency and accuracy of search. And In this part, I'm going to just briefly talk about how we perform data set discovery over using join operation. But before that, what's the connection of data set discovery to responsible data? Custom data sets, first of all, are very expensive, and it's rarely the case that we can find one data set that satisfies the responsibility requirements that we discussed in the first part of the tutorial. For example, if you consider a ticket data set, usually these data sets, traffic ticket data sets, usually these data sets do not contain information about the age and demographics of the drivers. But in order to be able to evaluate responsible data requirements like group requirements and scope of use and other requirements, what we need is to know the value for the sensitive attributes in data sets. And data set discovery provides us with tools for finding these sensitive values. For example, I can go to the data repositories and join my traffic ticket data set with other data sets that contain demographic information of drivers. So the goal of data set discovery is to provide us with sensitive values for sensitive attributes. So the first operation is that we consider is a join. So let's see how we can perform join. We can perform search based on join query. In this case, the user inputs a query table. And the user also specifies a column called query column. And the goal is to find, for example, top K of tables in data repositories that can be joined with the query table on the query column. For example, I may have a greenhouse gas emission data set as my query. And after performing data set discovery, on attribute geo, I can augment this data set with new features about the demographics of this geographical location. Note that in this specific join, some of the tuples may not have a match in the candidate data set, and in that case, we need to either discard the tuple or augment the tuple with null values. And our goal here is to basically minimize the number of null values that we have. We get in the result. So now the question is, what's a good measure for this side of data set search, where our goal is to do integration? What we want is to maximize the number of retained tuples after performing join. And that can be evaluated by computing the overlap of set of values in the columns that we join together. If I join a column X with column Q, the size of their overlap or the normalized size of their overlap by the size of, for example, query can give us a way of evaluating the level of joinability of these two columns. Remember that we want to be able to do search. So if I have a query with these three values, I probably rank locations column higher than the geo column due to higher value of overlap. So whatever data discovery, joinability discovery measure we consider, we can formulate the problem in two ways. It can be a threshold-based search where I'm given a query Q and a joinability threshold T star. And the goal is to find attributes X such that the joinability of X with the query is higher than this threshold T star. In the top K version of the problem, I'm given a query Q and a parameter K. And the goal is to find top K attributes X based on this joinability measure. Usually we can, in terms of solutions, we draw on some of the set similarity search techniques and information retrieval to solve these problems. When I talk about joinability measure, the syntactic joinability measures are containments or overlap. They can be also Jacquard. Semantic joinability measure, which tries to capture the problem with the transient data quality and dirty data in data repositories, is more sophisticated at performing simple overlap. It basically translates, represents two columns as a bipartite graph. And the goal is to basically find a matching with the maximum score. I won't have time to talk about semantic joinability measure. So that was an overview of dataset discovery when the query is a dataset or a column by itself. In a more in a different trend of dataset discovery work, or the new generation of discovery techniques, the focus is on feature discovery, and the goal is to find features that can improve the accuracy, the performance of machine learning models. In this specific task, we are given a target column and a join column from a query table, and the goal is to find tables that can be joined with the query table on the join column, and they contain some attribute or some column that is coordinated with the target column. So here, I'm joining my query table on column J with J prime of the candidate column, and I want to maximize the correlation between the targets, which is the class table, for example, C, and some feature in the candidate. And by correlation, some of the existing techniques consider Pearson correlation. So the interesting trick in this case is to build a synopsis on the data that enable the reconstruction of a uniform random sample of the join table. So the goal here is to basically build synopsis on pairs of categorical and numerical attributes on all the tables in the data repository, and index them efficiently, such and have a search algorithm such that I can join C with I can join J, which is a categorical attribute, with some categorical attribute in the synopsis, and maximize the correlation between the numerical values. Note that in the work that we, in a recent work from Sigma 2021, the goal is to design the synopsis in a way that they are random samples over the data, and in that case, if the data is biased, we can imagine that the random sample will be containing mostly the majority group. So here the goal is to design techniques that consider also the minority group and identify features that are unbiased and highly correlated with the target attribute of the query. I think I'm going to stop now because we only have 2 minutes and I won't be able to finish the next part. If there is any questions, I will answer the questions from people in the
I have a question. Because I worked on recommendation system, we
yes.
have some work about devising recommendation. So if you like devising ranking, so you have some recommendation, you have some recommendation for the user. So if you have some position bias or exposure bias or some popularity bias for this task. Yeah, actually, I have always have one question about maybe this scenario involves many stakeholders. Maybe the item loader, maybe the platform, all the users. Right? So it's a scenario with multi stakeholders. For the bias and the fairness issue, it will usually will only consider the user side. So maybe the objective or the bias ideal objective between these multiple stakeholders, it might be contradictory to each other. Maybe, for example, the platform may want more time from the user and expose more popular items for the user. But from user side, it's different. So how to handle this kind of scenario? What's the ideal by fairness objective we are trying to achieve?
All right, so for the people on the Zoom to just have an idea on the question is, if you consider recommendation system, in the recommendation systems, we're talking about two-sided fairness, and in general, multi-sided fairness, because there are multiple stakeholders, each of them have their objectives. One wants to maximize their sale, the other one wants to maximize their satisfaction of the user, etc., right? So how is it related to data, right? Or okay, cool. So I would like to go back all the way to slide number 2. Okay, in the meantime, note that, okay, slide number 2. All right, so note that in the pipeline of data, there are 2 products, data and algorithm. So what you're talking about is this part, the outcome of a recommendation system. It can be fair or unfair, right? So it has some connection to the data, but the connection is not direct. So it doesn't mean that if you have a data that, for example, it contains like enough users from different demographic groups, it's going to satisfy fairness both for the users and for the stakeholders, right? So that is correct. So, but all right. So practically speaking, by the end of the day, responsible data is not going to solve all the problems of responsible algorithms. The goal should be to minimize the biases, such that when you are designing the algorithm, you have good data to work with. And if you're careful about the type of fairness that you want to consider, you should be able to get to a trade-off. But I agree with you. The fairness measures contradict, right? And also, if you just add on top of it the multi-sided fairness, it's going to become an impossible task to satisfy fully for all users, right? Okay, I hope I could answer the question.
Yeah. Also, I have another question. So, based on your question, maybe some features will, just as you mentioned before, maybe some features will correlate with synthetic attributes, right? Mm-hmm. So, this kind of using this kind of features for prediction also will improve kind of bias results. So this yeah, we have done some work about using causal methods to debiasing or achieve better fairness. We found that when we try to design better methods to remove the unbiased effect from the results, okay, then it will, in most cases, it will hurt the performance. It hurts the accurate performance.
Right. Fairness is not free. We all know that there is a price of fairness, right? That's a metric that, like almost all of the papers related to fairness, if you check the experiment section, they have a plot for price of fairness, which is like to achieve the fairness that they're trying to achieve, how much they are sacrificing on the performance, right? So, yeah, I mean, everything is in trade-off with everything, right? Performance with fairness. Fairness measures with each other, fairness from the perspective of different stakeholders. But what is important is that we have to be responsible in our design, which means that we need to be mindful of all these things that are important at the same time, and then try to get to a balance. If you are interested, I have a blog post on Sigmod. It's called Enabling Responsible Data Science in Practice, and it fully talks about all of this and how to handle it. But you're right, nothing's free.
Nothing's free. Using that. Yeah. Thank you.
Hi everyone, welcome to the second part of the tutorial, the second half of the tutorial. At the end of the previous half, we talked about dataset discovery and how we can use dataset discovery to find sensitive attribute. In addition to the research on how to efficiently perform discovery, recent work studies what discovery queries to ask. Yes, now the slides are on Zoom, yes. For example, if an online app store has enough training data for certain slices of data, let's say American customers, but not for other slices of data, not other groups of customers, just collecting more data will only bias the model training. So it exacerbates the problem. And so the idea here is to have a balanced way of collecting data, and one of the existing work to do so is called Slice Tuner, that proposes a way of first identifying problematic features and values that cause bias. These combinations of feature values is what I refer to as bias. Slice Tuner also proposes a way of selectively acquiring data for these problematic slices and acquiring the right amount of data for these slices, such that the model accuracy and fairness on all slices are optimized. So at the core, Slice Tuner maintain learning curves for slices. These learning curves estimate model accuracy given more data. So it's basically, in reality, is model loss given more data. And based on these learning curves, Slice Tuner can extract some guidance about what slice is worth investing into. And the key challenge of building these learning curves is that first of all, they may be inaccurate when we don't have enough data for a specific slice, and second, there might be some dependencies between these slices that means collecting data for one slice may influence the learning curve of others. And Slice Tuner solves this problem by iteratively and efficiently updating the learning curves as more data is collected. So that was basically acquiring data and identifying discovering problematic slices. So now I would like to briefly talk about data cleaning. Collecting complete, clean, and correct data has always been a critical requirement for data processing. Regardless of responsible data cleaning is an important step in data integration. And this requirement becomes even more important and critical for responsible AI. And this is because, as we saw in the first part of the tutorial, incomplete and incorrect data typically hurt the minorities, and further increasing bias for minorities. The rich body of work on data cleaning in the data integration community has a lot to offer to the process of obtaining complete and correct data sets. An example of data cleaning work that targets at fairness issues is a library called FairPrep. This library is built on top of Scikit-learn library and AI Fairness 360. AI Fairness 360 is a library for understanding and detecting algorithmic bias. In Fairness Prep, what it does is that it promotes data to first-class citizens in fairness-related studies. FairPrep basically is an evaluation and design framework with fairness-specific metrics. The first insight that Fairness Prep provides is this insight about the outcomes of existing fairness enhancing interventions. For example, it shows that the high variability of the outcomes of interventions with respect to different split of train and test data has a lot to do with the lack of hyperparameter tuning of the models. And it also, another insight FairPrep provides is that the choice of data cleaning can actually, and missing value imputation can impact the effectiveness of the interventions that we have. And based on these studies and auditing existing pipelines, FairPrep proposes a general evaluation framework that has 3 phases. In the first phase, we learned the suggestion is to learn different models on the training set, considering various data transformation and cleaning techniques. So we consider all possible combination of cleaning techniques in the pipeline. And we evaluate using the training data. The second step is to perform hyperparameter tuning and compute performance using a validation set, and have a human in the loop setting where the user actually selects the best model. And finally, in the third phase, we compute the production metrics for user selected models on a held out test set. So that was basically an evaluation for fairness in intervention pipelines. So we will talk about data cleaning and some of our ongoing work in the third part of the tutorial. And at this point, I would like to talk about uniform and independent sampling over relational data. In general, machine learning on normalized data is inherently very expensive. Mostly because integration and particularly join operation on very large data set are expensive. But luckily in many applications, such as approximate query processing and learning, just having a random sample suffices for learning. So we don't actually need to integrate the data and then compute approximate answers, query answers, or perform learning. So when we have one source, obtaining this uniform and independent sample can be achieved by existing techniques, stratified sampling. Just we are given a set of sensitive attributes and an integer parameter k, and the sampling on a single data set guarantees that we have at least k tuples from each group. And if the size of a group is fewer than k, we just return the whole group. But that was easy for one single data set. The problem is not that simple when we deal with multiple sources, and we actually, to have all the features we want in one data set, we need to perform join. So TPCH benchmark, if you're is a well-known benchmark for the database community, and the example that I have here is based on TPCH benchmark. Suppose that our goal is to predict the return flag of an item shipped to a customer. And to do so, we are going to look at features of the items itself, and of the item itself, and features of the previous items that were returned by the same customer. So what I need is basically the information of the customer, the information of the item itself, and also the other items that have been returned by the customer previously. In order to write a query find a table that contains all of the features that I just discussed, using just a TPCH benchmark, we need to join 7 tables, including a join, self-join, and 2 very large tables. And self-joins are particularly very expensive and problematic because cycles in join cause the space of the data to blow up. So we get a very large number of tuples in the result as a result of cycles in a join path. So if we perform the full join of these 7 tables on an instance of TPCH, this may take hours to complete just the join operation. And training the classifier on the full data, let's say SVM and classifier on the full result of the join, is taking forever. One promising result here to mitigate the high cost of join and model training on this full data set is to basically obtain a random sample from the full join result. And basically train the model on this random sample. And it's been shown that if, for example, we obtain a very small subset of the full join result, let's say 200,000 samples from the 17 trillion tuples in the full join result, the accuracy converges to almost accuracy of considering the full data. So basically here, the accuracy of the model on the full data is roughly 76%. The remaining 24% error is the inherent error of the model itself. And this accuracy can be achieved by just a random sample. So now the question, the bottom line, that random sample, that IID sample, without performing the join, but directly going to the base in the join path. So just to define the problem a little bit more concretely, we are given data sets T1 and T2, and a sampling algorithm A is IID if tuples returned by this algorithm all have the same sampling probability, and the appearance of two tuples in the join result are independent events. So note that here we are concerned with satisfying the first requirement that we discussed, which is the underlying distribution requirement, and we don't care about the group distribution requirement at this point. So, for example, here I have two relations R and S, and as a result of joining them on attributes B, natural joining them on attribute B, we may get 10 tuples, and we want the sample of if I sample from the result of the join, I want the probability of each tuple being in my sample to be 1 divided by 10. And of course, I want independence between tuples. This is the problem of IID sampling over join goes back to the 90s, and it was studied in the context of query optimization because random sampling over join is one step towards estimating the size of the join, which is an important step in ordering joins as well as query optimization and running the query optimization algorithms. So there is a large body of work in this area, and there are some interesting results for random sampling over join. The first result is that if I sample base relations independently and then join the samples, the size of the join of samples is going to be exponentially smaller than a sample from the actual full join. So if we create synopses of base relations, for example, base relations R and S offline, and we join them, we cannot expect a very large join results. The second important result is that sampling cannot be pushed down in join. So this means that if I obtain samples from two relations R and S and then join them, the result of the join is uniform, so each tuple has uniform probability, but it doesn't guarantee the independence requirement. So let's look at an example, a way of obtaining samples from join and sampling from base relations and joining them. So let's say I use Bernoulli sampling with probability P for obtaining some sample from relation R and relation S. And here I'm sampling relation R and S in my join path. So the probability of obtaining a tuple from relation R is P, and the probability of a tuple from relation S is also P. So the probability of a joint tuple after on the samples is going to be P squared. And that can be we can show that every join of samples that we get has this probability. So we have the uniformity. Looking at the independence, let's assume that I have two tuples T1 and T2. T1 is coming from sample of R, and T2 is also coming from S, a sample of S. And the probability of having the join of these two tuples in my final result is P squared. If I know that the join of T1 and T2 exist in my join results, the probability of having the join of T1 and T2 prime is going to be P. Note that the T2 in these two cases is the same. And clearly we can see that this is because as a result of knowing T1 and T2 are in the joint result, I know T1 is in my sample. Therefore, the probability of having the joint of T1 and T2 prime is just a probability P. And you can see that here, basically, we cannot guarantee independence. So a simple Bernoulli sampling and then joining the samples is not going to give us IID sampling. And in the literature, since the 90s, there are different ways of solving this problem. The problem has been specifically studied for two-table joints. Then special case of the problem that considers a multi-way joints, but just the kind of joints that are just primary key and foreign keys were studied. And so later, the idea of approximate query answering, for example, computing aggregate functions such as sum and average over join, was studied extensively. Two examples of work are ripple join and wonder join. In these cases, again, the approximate query answering is done by obtaining a sample from the join, but neither of these techniques guarantee IID, but they have a way of using non-IID samples for unbiased approximate query answering. For example, ripple join returns a uniform sample, but samples are correlated, and wonder join returns independent but non-uniform samples. So there is a more recent work that provides a solution for generic joint paths, all sorts of joint paths, cyclic, acyclic, and chain joint paths, and it has a way of basically guaranteeing independence and uniformity. So I'm going to go over this technique quickly. Basically, in this work, we represent a joint path with a data graph. Here you see a data graph for a chain joint on R1, R2 to Rn. In this data graph, which is a directed acyclic graph, each node is a tuple, and an edge between two nodes shows that these two tuples can be joined together. For example, relation R1 contains attributes A1 and B, and you can see that if you see my cursor, this tuple with value 1 and 1 can be joined with value 1 and 3. How can I add cursor? Yes. Yeah. Thank you. So here, this is a tuple from relation R1 with attributes A and B, values 1 and 1. And this is a tuple from relation R2 with attributes B and C. Join these two relations, R1 and R2, are joined on attribute B and B. So this is a natural join. And we can see that there is an edge between these two tuples. So each node in this technique is associated with a weight. The weight of a tuple is basically the number of joint results that are yielded from that specific tuple. So the weight, and it's normalized based on all of the weights in weights of tuples in that relation. For example, let's assume that somehow I can compute the number of tuples yield from this specific tuple, which is, for example, 5. So 5 tuples in the result of this joint are starting from the tuple that I'm pointing to. Then the weight of this specific tuple in my relation R1 is going to be 1 divided by 3, normalized by all of the weights of all other tuples. In each tuple, we are going to sample tuples from relations one by one along the joint path. And each tuple is sampled based on its normalized weight. So that means the first tuple here is sampled with 1/3, the second one 1/3, and so on. Once a tuple is sampled, we investigate the next tuple in the next level in the next joint, and we again sample based on the weight of that the weight of that tuple. For example, if I sample the third tuple, then I'm choosing between these three tuples. And for example, let's say the middle tuple is sampled by probability 1/3. But obtaining these weights accurately is actually requires looking at the whole data and performing the join in practice. And the goal of this work is to basically come up with different upper bounds for the weights. And because we use the upper bound, we need to add an accept-reject ratio step in order to guarantee uniformity. And the whole point here is that the tighter the upper bound, the lower rejection ratio we have. Therefore, we have less latency. All right, so that was, we're going to visit random sampling over join later in our future work.
All right, so I'm going to continue with the next part of the tutorial. It's a shorter part, but it's an important one, and it is related to data profiling. So if you remember when we were talking about the responsible data and the requirements that the responsible data has, we talked about augmenting the scope of use for data. That is like, if you are to use this data, what are the limitations and for what tasks you have to use it and for what not, right? So recently, there has been an interesting concept called nutritional labels for doing so, and it is a specific case of data profiling. If you are interested, Siavash Abedian has a very nice book related to data profiling. But nevertheless, so our focus is on nutritional labels, and again, there is a very interesting paper by Bill Howe and Julia Stojanovic in Data Engineering Bulletin 2019, which talks about nutritional labels in general and specifically for algorithms and data. But what is a nutritional label, right? A nutritional label for food, every time we buy food items, we just see that on the package there is a small label that shows like the critical information we need in order to make a decision whether or not this is like the right product for us, right? So what are the ingredients, like how much is a calorie, etc., right? So the analogy has been drawn from the food industry, and the goal is to specify a compact label containing most critical and important information shown in form of some visual widgets, where every widget contains some standardized information about fitness for use for the data or the evaluator. And the example of the nutritional label for data sets is Mitra label. And it's a system for just generating the labels for data. Here I have a screenshot of the system where it generated a nutritional label for the Compass data, right? So for those of you who are not familiar with this recidivism risk data is a data set of criminals that has been used with Probablica. It's a popular data set for fairness ML, right? So it generates a nutritional label. So, and for that, you need to specify some of the attributes or few information you have to provide before the label is generated. For example, what are the attributes you want to focus on? What are your sensitive attributes? Or if you want to pick the widgets yourself, etc., right? And then when you do the generate, it behind the scene, it solves the NP complete problem, and it finds like what are the more important widgets. And here in this example, the nutritional label contains some overall overview of the attributes it believes are important, some of the distributions. The functional dependencies are related to the third requirement, the unbiasedness of the features, right? So if, for example, there is a functional dependency between age and, let's say, salary, right? Then that shows like the bias in the data. Okay, so the second widget in this example shows is related to the second feature, to the third feature, which is bias in the features. And the last one is related to data representation. Earlier and during the tutorial, I talked about MUPs, maximal uncovered patterns. And in the context of Mitra coverage, I already talked about that feature, which identifies the uncovered parts of the data. Okay. And the other type of data profiling or data augmentation, a famous one, is called data sheets. And data sheets consist a set of questions about how the data is collected and what have been the motivations behind creation of the data, which basically sets the goal for what should be the latter uses of the data. Okay. And with that, I guess we're going to switch to part 3, and that is fairness aware and distribution aware data integration.
So in the third part, we're zooming into the research design for data collection and distribution aware and fairness aware measure. We're going to focus on data collection techniques that have distribution aware and fairness aware measures in mind. And we're going to mostly focus on those groups of work that focus on group representation requirement. And we will also going to talk about fair query answering that does not for the kind of data that does not satisfy underlying distribution requirement. All right. So a scenario where distribution requirements have been studied is a crowdsourced entity collection. In crowdsourced entity collection, the crowd is asked to complete missing data in a data set or a knowledge base. And usually users in such task have some distribution requirement in mind. That they want, and this distribution requirement is on the entities that they want to collect from the crowd. For example, a university wants to find faculty candidates from the job market, and the university is likely to have an expected distribution on the specialization of the candidates as well as the demographics of the applicants. So another example of this style of crowdsourced entity collection is in point of interest collection, where the task is to ask the crowd to submit locations with additional information. Let's say roadside parkings. It's an example of this additional information. And naturally, what we want is to have this point of interest to be uniformly or evenly distributed in an area instead of having skewed spatial distribution over a specific location. And because we're dealing with the crowd and crowd has open world nature, each individual worker may have its own bias of data collection and answering to the requests. So what we want is to have an effective and adaptive way of selecting these workers such that we can achieve the data distribution that we have in mind. And this is basically the goal of work such as crowd deck. This work aims to find the best crowdsourcing strategy that makes the collected data satisfy the distribution requirement as much as possible. And the goal here is to basically minimize the difference between the data collected from the crowd and the expected and desired distribution. And as you can imagine, the approach is iterative. It estimates the underlying entity distribution of each worker on the fly based on the observed entities that the worker returns or submits. And then we have an optimal way of selecting the set of workers such that the entities that they return minimize the difference between the distribution of collected entities as well as the entity and the desired distribution that we want. And we need to, of course, because distribution and bias of the crowd is unknown, every time that a crowd worker submits a job, we need to basically update the distribution for that specific crowd worker. So now I would like to talk about data distribution tailoring. Usually we find, when we collect data, we find ourselves in scenarios that the data is used for some downstream learning task. And if you remember this example from the beginning of our tutorial, that in this case, just having a random sample from the underlying distribution may not result in a poor model overall, but may result some poor outcome for certain slices of the data. And in this case, only acquiring more data only makes the problem worse. And what we want to do is to have a more balanced data distribution over different groups. And by groups, we mean, by group distribution, we mean the discrete distribution over groups. And these distributions are counts over these groups. Groups can be independent variables, for example, different salary brackets. They can be dependent, like having success and failed loans for different demographics. These groups can be protected groups, race and gender and so on. They can be even class labels, or they can be rare outcome groups, for example, accidents, when we want to, because they're rare, we want to oversample them. Where do we get the distributions that over these groups? This distribution can be obtained after the fact during model debugging. For example, we find the slices of data for which the model underperforms, or we can use the data coverage measures that were covered in the first part of the tutorial and then be more proactive about these distribution requirements. Because custom data is expensive, the user often relies on external sources for obtaining data and collecting the data. And these external sources could be data lakes, they could be crowd, or they could be data markets. So now the question is how data from multiple sources can be combined in a cost-effective way to find the target data set that fulfills the distribution requirements. So a little bit more specific, we have the target data set has some schema. Let's say that the schema is described with a collection of attributes. Some of these attributes are identified by the user as sensitive attributes. The sensitive attributes, the combination of the values over sensitive attributes gives us groups. So the set of groups we deal with are predefined. And we are also given a collection of sources. At this point, let's assume that the sources contain the same features that the target dataset has. And so that means they either have a sensitive attribute explicitly defined in their schema, or we have a way of identifying these groups for these from the tuples of these data sources. This could be done by Wix classification, for example, to label these data points with sensitive attributes. So we are also assuming a tuple at a time access to sources. And so it means that upon selecting a source, we can obtain a k-sample of the sources. And acquiring these samples could be associated with some monetary cost or the cost of computation. For example, if the sensitive attribute doesn't exist and we need to label, the cost of labeling is the cost we consider. Or even the investment into the crowd is also the cost we can consider. The cost is specifically interesting in the setting when we have data markets. And data markets, on one side, we have data providers that are data publishers, enterprises, and businesses that are willing to publish their data and share data once they're incentivized by some monetary reward. And on the other side, we have data buyers, such as news agencies and data science companies that are willing to pay and buy some data with some monetary cost to do their data-driven task. And just if we only think about data consumer, from the data consumer side, the goal here is to obtain the data that they want with the distribution and schema they want and minimize their cost of data collection. So to define this distribution tailoring problem, we are given sources with their cost. We're also given count requirements over predefined groups, and the goal is to select a sequence of sources to sample from such that count requirements are satisfied and then expected total query cost is minimized. So the sequential version of distribution tailoring selects a source at each iteration and then obtains a sample from the source, identifies the group, and checks whether the group is, if the sample belongs to the group that we care about. Yes, keep it, otherwise discard it. And then it may update some aggregate or knowledge about the groups in the sources. And the whole goal is to have this source selection designed in a way that we have minimum cost. So there is a direct way of solving this problem by defining a cost function and solving the, for example, dynamic programming problem or modeling the problem as LP. But that's very cost effective. I'm not going to get into the details of that, I guess due to time. But there is a direct way of solving this problem by designing strategies for source selection. So the direct way of solving the problem and optimizing the cost exists, but it's not efficient when the count requirements are large and the number of groups is large. So we're going to design strategies for source selection. So the question we ask ourselves in designing these strategies is how much do we have knowledge about the distribution of the groups in data sources. I'm going to first talk about the case of known distributions and when we have some knowledge about groups. So one way to think about the problem is to decide which group we want to focus on in each iteration. And it turned out that we have to, at each iteration, focus on the minority group. And by minority group, I mean rare groups and the groups that are expensive to find. Our algorithm has this round robin with priority strategy on groups algorithm, where at each iteration we select a group in a round robin fashion. And we select a group with the highest priority. I'll explain the priority later. And then for the selected group, we find the best source for that group. The best source for a group is the one that can give me samples from that group at the lowest cost. So that source has a high fraction of the group that I have selected. So it means that if I sample from the source, it's very likely that I get something from the group. And that source is also cheap. The priority of the group is basically the expected cost per sample of the group if its best sources are selected. So it turned out that if we have only two groups and the cost for all models is equal, the strategy of selecting the minority group is optimal. But if we have the generic case where we have multiple groups and arbitrary cost models, the result is suboptimal, but there is a way of bounding the result based on the size of the data sources and also the distribution of groups in each data source. So just to give you a very small example, because the cost of, remember that the priority was expected cost of obtaining samples from a group if its corresponding best source is selected. So that means the cost of the best source divided by the probability of the group in the best source. And because the cost is equal for all data sources in this problem setting, we're basically obtaining, we're going after the minority group. And here in this slide, I have a simple example of what happens when we go after the minority. Let's say I have two groups, G1 and G2, and D1 is the best source, the cheapest source for group G1. So it means that this is the cheapest way of obtaining samples from G1. And D2 is the best source for group G2. Let's assume that D1 has 20% of G1 and 80% of G2, and D2 has 5%, only 5% of G1 and 95% of G2. Our strategy says to basically go after group G1 and select a sample from D1, and that's because if I pay the same cost, so let's say with the same cost of 5 samples, if I select a spend it on D1, one of them is going to be from group G1 and the rest are going to be group G2. And remember that we always keep the samples that are useful. So if I'm looking after, going after G2, I'm paying the cost of just one G1, but keeping the 4 G2s. And if I select D2, everything I get is from group G2, and there is very small chance of obtaining G1. So the whole point here is that if I go after the minority, I'm collecting the majority at no cost. And here we're showing just some examples for the case of that we're varying the number of data sources. And here we see on the x-axis the number of data sources, and y-axis the cost of and number of samples of collecting the same number of tuples or samples from all 4 groups that we assume. And the interesting message here is that when we have a larger number of data sources, we have lower cost for DT, is because there is more chance of obtaining a data set that is useful. The right plot is basically studying the cost and number of samples versus different distribution of data in different data repositories. Let's say we have only 2 groups, G1 and G2, and each group of bars you see here is one data repository. The leftmost one says that only 1% of these data sources in the repository have group G1 as a majority. So it means that the DT algorithm selects that one good source for obtaining G1. And if I compare it to a random source selection, which selects sources at random and samples from them, that algorithm, that random source selection, will have probability of 1 in 100 to select the best source. So that explains a large gap between the results. If if half of the data sources have G1 as the majority, the random selection becomes a good strategy. It has no overhead, and the cost becomes very close to the optimal, to the case of binary DT. And the message here is that random source selection could work if there are multiple data sources that contain the groups as a majority, which is not always the case in practice. For example, we usually have one group to be the minority. If we look at employees from different tech companies, female employees are a minority. So that was when we know the data distribution, and we can leverage the knowledge. What if we don't know the data distribution of the groups? The DT algorithm has no choice but exploring different data sources and hoping that in some settings it can find a good source by just exploring. And what I just explained sounds a lot like a multi-arm bandit problem. In the multi-arm bandit problem, we are given a time horizon T, and we have a centralized planner that sequentially chooses actions or arms or in this case, data sources. And at each, upon choosing an action, it receives a stochastic reward from an unknown distribution. And the goal of the planner is to basically minimize the regret. The regret is the difference between the reward that the algorithm obtains and the optimal reward totaled over the time horizon. And usually in practice, for bandits, the optimal regret is square root of the time horizon. There are some log parameters here hidden here. So the problem that the DT is facing in this scenario is to basically balance the exploration and exploitation phases to optimize this regret. There are different ways of doing this in the literature. One way of doing it is epsilon greedy. I'm representing a reward function for the epsilon greedy multi-arm bandit for DT here. In this strategy with probability epsilon, the planner explores. And with probability 1 minus epsilon, the planner exploits. During the exploration, the planner samples a random sample, selects a random source, and obtains a sample and processes a sample. And during the exploitation phase, the planner basically is acting greedily based on some reward function and obtains some sample. In both phases, when we obtain sample, we update the probability and the distribution knowledge about groups in different sources. So how does the DT planner performs during exploitation? We have a two-phase policy. So again, in this case, we're prioritizing, we're trying to find a group that we want to focus on and prioritize. We prioritize the group that for which the remaining count requirement is very large. So it means that I have a very long way to get to satisfy this group count requirement. And the group that is has basically is cheap and it's very it's the ratio of that group in our specific its corresponding source is low. So we're going after, again, the rare groups and the groups for which a lot of the count requirements are remaining to be satisfied. Once we select a group, we find the best source for that group. Again, the source that, based on our knowledge, has the highest ratio or fraction of the group, and also it's cheap. And if we apply this two-phase policy, and our analysis shows that an epsilon greedy strategy that performs exploration with epsilon probability of a third root of ln of t divided by t at time t, so we're decaying the epsilon, we'll have a regret of t to the 2/3 log of t to the 2/3 at time horizon t, for the case that we have equal cost for all of the sources. And this, you can see that this regret is not that far from the optimal regret that we were looking for, which was a square root. And note that in this case we cannot apply upper confidence bound, which is a better strategy. So that was also how we tailor the distribution of specific data set using different data sources. We are also touching upon a recent work that adapts to the required distribution of the data for ML in an online fashion. This work, which is data acquisition for ML, basically is defined in the data market setting that I described before. Again, here in this setting, we have a data provider that makes their data available at some cost, and we have a data consumer that wants to buy this data to train a model. And so the assumption here is that the provider maintains a collection of data records drawn from some target distribution. which is initially entirely unknown to the and invisible to the customer and the consumer. The consumer also has a machine learning model already trained on some data that follows the target distribution, the same target distribution. And although the data of the provider and the data of the consumer are from the same distribution, they may not be necessarily representative. So that means the provider may have data from some part of the data and the consumer may have data from another part of the data. And the goal of the consumer is to train a model on a data set that represents a distribution, the target distribution. And this is done by tying together different pieces of samples of the data from various slices of the data to get the distribution that they want. So there is this strong assumption that the provider and data consumer are having this same target distribution. And the ideas that the paper proposes is, again, based on exploration and exploitation. It specifically proposes an estimate and allocation solution. So at the beginning, the algorithm allocates some budgets and uses that budget to estimate the distribution of the data in the data of the data provider. So here the goal is to come up with a sequence of predicate queries to obtain the data. For example, in this specific case, the predicate query could be that, for example, return 30 records of employees within certain age and certain salary. So what we want is to come up with a sequence of these filtering predicates. And at the beginning, the algorithm allocates some budget to estimate the value or utility of each of these predicates. The way the utility is defined is based on the contribution of the data we obtain from the predicate on the accuracy of the model. But this accuracy requires model training. And we want to avoid that. So what the paper does is that it defines a utility based on some proxy. And the proxy is how novel the data is, the data we obtain based on a predicate. And the challenge with that is the notion of novelty is dynamic. So as I collect more data, due to redundancy, a predicate that would give me novel data is now giving me just redundant data. So the idea of the basically this algorithm is to have some allocation phase for the budget and then monitor the changes in the utility of each predicate as they're collecting the data. So in the next part, we're going to talk about fairness-aware query answering and the kind of data that doesn't satisfy underlying distribution requirement.
All right, so yeah, we're continuing on how to collect the data responsibly, or right, so fair data integration. Okay, I want to make connection to the first part of the tutorial that we talked about how to collect the data that is representative of different demographic groups and representation bias. And if you recall the taxonomy, to resolve representation bias, if you have the option to collect more data, you can do data integration similar to what we talked, right? So if you have more sources that you can collect data from those, then you can smartly collect the data, right? But what if you don't have the option of data collection, right? You are given a data and that's what you have, right? And then how can you be careful with using the data? So one of the operations on data is query answering, especially selection query answering, right? So you have a large part of data. Let's say you have a large database, and from that database you have a select query, and on that select query you want to do something. And to give you a concrete example, let's say a company, they have employees and they want to focus on their elite employee, and obviously salary have a correlation with being elite. Basically, like if it's merit based, the elite's employees' salary is going to be higher. So what they can do is that they can conduct a select query on their data and filter on employees that their salary is above a certain threshold, and then survey those, and then yeah, that's what they're going to do. All right, keep this in mind. Now back to query answering. So fairness aware query answering, the literature is divided in two parts. One is query rewriting and aggregate query answering. And aggregate query answering, you want to the query is of form of, for example, what is the sum of this, or what is the average of this, right? So there are some aggregates that you want to satisfy. And but in query rewriting, it's a type of select query that the actual tuples are the return of the query. Our focus is on the first part, right? The query rewriting, and it's aligned with the example that I gave you. So back to the example, the company is going to issue this query, select all of the employees that their salary is more than 65K, and those are considered to be the elite, right? But we know that unfortunately there is the gender bias in the salary, and historically speaking, the salary of the female employees are less than the male employees, and if the company is not careful in this, their select query may return only male employees, and therefore if they, for example, take surveys from their selected employees, it's only the need of the males, and they're going to only satisfy the need of those, for example, buying some new stuff or creating some new buildings, etc., based on what males need, completely ignoring the other gender, and therefore losing their female employee and further increasing the gender gap in their employment, right? So this is not something that the company wants. So let's say that the company is aware of this, and they want to, instead of only focusing on the ones that have a salary more than 65K, they are okay with minimally changing the selection queries, such that, first of all, the Jacquard similarity between the output of the two queries are the same, which means that almost the same set of people selected as the elite are going to be selected by the two queries. And at the same time, the selected range is representative. And in this case, we are looking for representation rate, which means like we are looking at almost equal rate of the two groups. Okay. In this line of work, the way that I'm going to present it, we are going to be limited into two groups, and one I'm going to show for visualization purposes as blue and the other one as red, right? So keep in mind we have two groups. And all right, so the queries can be in form of select from the database, where some range predicates are satisfied, subject to the difference between two groups. The weight, it can be weighted, is less than an epsilon, and the similarity is larger than a value tau. For example, we want to find the employees that their salary is larger than 65K, subject to the number of males, to the difference between males and females is less than 0.1, and that's obviously the ratio, and their similarity is more than 0.75. And that is Jacquard similarity, okay? So then the question is, how can you answer this query? In other words, how can you minimally change the initial query, the initial range, the salary range, such that the requirement of male to female ratio is satisfied, and the similarity between the output of the initial query and the secondary query is high? Okay, in the interest of time, I'm going only to focus on one specific case where it is unweighted and I only have one predicate, right? So I'm looking into single predicate range queries and the case that is not weighted. One important observation in this case is that it turns out the output is going to be a range that has a disparity of exactly delta, right? So the question is to find a difference ratio of at most delta, but it turns out that the most similar one has a disparity of exactly delta. Okay, so that's the first observation. And now with this observation, we can construct data structures that can help us quickly find such a case. In particular, we know that if we sort the data and we construct the cumulative sums, we can use binary search, and binary search is done in logarithmic time, right? So this high-level idea enables creating something we call jump pointers, where from every pointer in the data, let's say from the current point, you want to find the next point or the next range that gives me one more blue or one more red. The jump pointers are going to give that to us. All right. So let's jump to the details with an example. In this example, let's say the tuples are as I have on the right-hand side. And let's say that I have two attributes, A0 and A1. I want to only focus on A0. The idea is that first I need to construct this cumulative sum at each location. By cumulative sum, I mean like what is the difference between blue and red up until this point? From the beginning up until this point, what is the difference between blue and red? And then I'm going to use this cumulative sum to efficiently construct the jump pointers, as I'm going to explain. And then I'm going to use the jump pointers to efficiently answer those queries. Okay, so on that example, what I'm going to do is that first, I'm going to sort the tuples based on their values on attribute A0. In the middle of the slide, you're seeing the tuples sorted based on A0. I don't have the table here, but you can later on verify that. Okay, now the cumulative sum. If we look at the very left of this list, T1, it's a blue, right? It's a red node, right? So what is the difference between blue and red here? It's -1, right? It has one red, no blue. And then if you go to the second one, we go to T5, we have observed so far 2 reds and no blue, so it's a -2, and then T9 is a blue, so it decreases the disparity to -1, and then so you get an idea how these numbers are calculated, right? Okay, so that's the first step. We're done with the first step. We have the cumulative sums. Next is to create these jump pointers. And what is the jump pointer? For example, from the point, the beginning, which is the very far, I want to see what is the next point that gives me one more blue. Currently, I haven't seen any red or any blues, so the count is equal to 0. I want to see where is the point that I have the number of blues is observed so far is more than one more than the number of reds. And you can verify that where this pointer is pointing is a place that I have observed 5 blues and 4 reds. So number of blues is 1 more than the number of reds. And then from here, the jump pointer is giving me the place that I have. Currently here I have 1 red, 0 blues is a -1, right? So it points to the place that the sum of the reds and blues is equal to 0, and it's here. And again, you get an idea on how the jump pointers are constructed, both forward and backward. Okay. The construction of the jump pointers can be done in the order of n log n. Why is that? That's because for every point I'm constructing the jump pointer, forward and backward. I have 2 colors, and I have forward and backward is 4, so I need 4 indices. For every index, I'm spending log of n to do the binary search to find the next position on the cumulative sums. So it's exactly 4 times n times log n, right? So that's the time to construct the jump pointers. And now that I have the jump pointers, it's interestingly, it's very efficient. Then we can practically, in the order of log of n, for every range, we can find the most similar fair range. For example, let's say that this is the range, the initial range that is specified by the user, which is like A0 between 4.4 and 7, which if I look at the value, this is the range, this is the output that I get from T4 to T12. Okay, so if I look at this, I have 3 blues and 1 red, so it doesn't satisfy the representation rate. And I want to see how I can minimally change my range predicate such that I get the fair output. Okay, so now to see an example, you note that from the very far right of the query, from the right boundary of this range, which happens to be T12, I can do 2 jumps, 2 red jumps, right? To add 2 reds to my query, and it gives me this bigger query. And you can verify that in this bigger query, I have the number of reds and number of blues are equal. But is it the only way that you can get a fair range? The answer is no. There are different ways. For example, you can expand the left-hand side by 1 and the right-hand side by 1, and that gives you a fair range. You can also go 2 rights, right? That gives you another fair. Or you could go 1 red to the right, and from here, you could go to the right such that you decrease the number of blues, right? So if you go to here, if you go to here, you decrease the number of blues by 1. So this range from here to here has 2 reds and 2 blues, right? So you see, like, there are different ways you can expand and shrink the left and right boundaries of the query such that you get the fair query. Okay. Interestingly, we can limit this exploration space. For example, if the disparity is equal to 2, we know that the maximum we need to go to the right is 2 jump pointers to the right, to the left, and also 2 jump pointers to the right. That gives us a window. And within this window, we start from the very far left of, at a very high level, I'm explaining the algorithm. We can start from the far left of the window and then go to the far right and sweep the fair window here. And among the possibilities, select the one that is the most similar to the initial query. And it turns out this can be done in the order of log of n plus disparity. And if disparity is a constant, which is usually the case, it turns out the query time is in the order of log of n. So we have a very efficient algorithm for this case. And unfortunately, extending this algorithm for the higher dimension is not possible. There are some other algorithms based on transforming the query space into a graph and then graph exploration. Ideas such as A-star algorithm, but in the interest of time, I'm going to skip it. Okay, so all right, so with this, we get to the last part of the tutorial, which is the opportunities. So far in this tutorial, we talked about responsible data, right? What do we mean by responsible data? What are the requirements that data should satisfy for being responsible, being called responsible data? We talked about how we can use data integration techniques to be responsible in data collection. We talked about in cases that data collection is not an option, how we can use query answering for satisfying, for getting responsible data. But there are a lot of opportunities left. Just here, I mean, a crude way of seeing opportunities is to consider this bipartite graph that in the left bipartite, in the left partite, I have the requirements we mentioned, right? So distribution representation, group representation, unbiased and informative features, completeness and correctness, and fitness for use. And in the right-hand side, consider some tasks in the pipeline of data, right? The third slide in this tutorial. And we have data and feature discovery, we have data cleaning, we have data sampling, query answering, etc., etc., etc. And every edge in this complete bipartite graph is potentially a line of work. And unfortunately, and from the other angle, fortunately, most of these edges are first meaningful and second unexplored. So it means that there is opportunity for a lot of work here. And just to show you some example, in this part of the tutorial, we're going to explore a little bit more on some of these edges. So for example, consider data and feature discovery, be it requirement 2 and requirement 3 being group representative and complete and unbiased and informative features. The question is, how can we satisfy data that is both representative of groups and also it gives us unbiased and informative features. Okay, so that's one possible line of work. And for that, we are going to switch to random sampling over unions and joins.
So, in the second part of the tutorial, we talked about obtaining a random sample from join path. But the problem doesn't stop there. Let's assume that we have a company and we want to build a model that applies some promotion over the future purchases of customers by looking at bundle purchases and orders of the customers. And obtaining the features for this task requires joining multiple tables or even self-joining and having samples in joins. Let's assume that this company has databases in different locations. For example, one for the West Coast, one for the East Coast. And each of these databases have different relations tables and different ways of joining them. So in this case, in order to train a model, I not only need to perform join, but also need to perform a union over the result of all of the join and then perform model training or use the data for answering some union of conjunctive queries to get some results. For example, in this case, I may say, what's the approximate average age of politicians in European countries? So in both join and union operations, as well as the training or could be very expensive. So what we want to do is that instead of computing the full data, we want to be able to obtain a random sample from the union of joins. So more formally, we are given a set of joins. And we want to return n independent samples S from the union of these joins without performing the operations themselves. And we want the probability of a tuple T in the sample to be 1 divided by the size of set union. As we saw, random sampling over join is a very well studied. So we saw there that one solution that was explored is to obtain samples from the base relations and join the samples. So now the question is, why not we do the same for union of joins? And with a very simple example, I'm going to show you that this doesn't have uniformity. So let's say I have 3 join paths, J1, J2, and J3. They may or may not overlap. And I'm going to obtain samples, random samples, let's say using one of the existing techniques from each of these join paths. And the samples may or may not overlap. And then I'm going to union all of these samples. So now if a tuple R is in J1, in the join path J1, in the result of that join, but is not in J2 and J3, the probability of that tuple being in the union of samples is 1 divided by the size of join, 1. But if that tuple instead is located at the intersection of J1, J2, and J3, the probability of having that tuple in the union of samples is going to be different than 1 divided by join. And so basically, a simple union over joins is not going to give me uniformity. There are ways of adjusting the probabilities by having an accept-reject ratio based on the size accept-reject ratio. But what happens is that in that case, I need to know the size of each join as well as the size of the union. And knowing the size of the union means I have to know the size of the overlap of all k combinations of the joins, because it's a SAT union. So our framework for obtaining a random sample over union of join consists of a warm-up phase where we estimate the parameters that we just described here, the size of the join and the size of the SAT union of joins. And then we have some strategies for selecting joins at each iteration. Let's say we select each join with Bernoulli probability of the size of the join divided by the size of the union. Note that these parameters have been estimated in the warm-up phase. And then once we select a join, we obtain a random sample from that join. And in this case, we can guarantee that we have uniformity. However, it's difficult. What we need to do is to basically approximate this fraction, this probability for selecting joins. And to do that, we need to basically define a bound, an upper bound for the size of SAT union of joins. The tighter that bound, the lower the probability of selecting the join. The higher the probability of selecting a join, therefore we're reducing the latency. So the whole point of this framework, efficiency of this framework, is on how tight our bounds for the size of the join and the size of the SAT unions are. And here we have a trade-off between the cost we pay upfront for the parameter estimation and the latency that we get during the join selection and random sampling. So it turned out that the size of SAT union can be estimated using the smaller unit statistics called K-overlap. The K-overlap of a specific join is the number of tuples in that join that overlap with exactly k minus one other joins. For example, if I consider join path 1, the 2 overlap area for this J1 is going to be the green area. The tuples in the green areas overlap with exactly one other join. And it turned out that we can show the K overlap can be computed backward from K plus 1 overlaps. And in our paper, we have a way of computing these K overlaps for all types of joins, including chain, cyclic, and acyclic joins. So now, how we do the parameter evaluation, we have different ways of instantiating this framework. For parameter evaluation, which is estimating the size of the join and estimating the SAT union of joins, we have a direct way of estimating the parameters using statistics, which is a histogram of the data, which is basically what's available to most of query optimizers. This bound is biased, especially when we have skewed data. So it could be very loose when we have skewed data. We have another way, which is by performing a random walk over the data graph of relations. The random walk technique is unbiased, gives us unbiased estimation of the parameters, but it requires direct access to the data. The direct method, which uses statistics, is appropriate for settings such as data market and enterprises where such statistics exist, and we don't have access directly access to the data. The random walk is appropriate for more centralized setting, and the more sample we obtain, the better our confidence intervals are. Once we approximate the parameters, we have we have different algorithms for joint selection, and there's always a trade-off between the latency and upfront cost of the warm-up phase. So to overcome that cost of warm-up phase, our algorithm, we have an online union sampling algorithm that combines this parameter evaluation with joint selection and random sampling. So it means that we sample during, for example, random walk, we sample joint path, and then we reuse those samples during the random sampling over joint path, and then we revisit every time that we update these parameters. We revisit all of the samples that we have collected, and with some accept-reject ratio, we adjust their probability such that it becomes 1 divided by the size of U. So that was random sampling over union of joint. The first future direction that we're presenting here is on data cleaning, auditing cleaning algorithms. Data cleaning algorithm is so data cleaning is an important task for satisfying correct and complete data requirement that we discussed, the fourth requirement, and auditing these data cleaning existing data cleaning techniques is an important task for responsible data. This requires even defining task-specific fairness measures. For example, for the case of a missing value imputation, we may have to define notion of fairness for the specific task of missing value imputation and evaluate the fairness of the existing imputation techniques. One specific problem that we're working on is the fairness over entity matching, and which is basically the task of auditing the existing entity matching techniques. What's an entity matching technique? In this task, we are given two sets of entities A and B, and entity matching problem is the problem of identifying all correspondences between entities in A cross product with B that correspond to the same real world objects. And for example, here I have two data sets consisting of authors and their affiliation. And for example, author A2 and B2 refer to the same entities, and it's just a change of name for a specific person over time. Authors A1 and B2. So we compute the case of match and non-match for all pairs of tuples in these data sets. And what happens is that you can imagine this is basically a special case of classification task, because we're assigning each pair to a match or non-match match class. Usually assuming that the size of each data set or set of entities is n, you can imagine that the number of possible correspondences is very, very large. And what happens is that we usually have very few matches. So the number of matches in our correspondences could be linear in the size of data sets, while the space of all correspondences is and a square. So usually in the entity matching task, we have a blocking technique which tries to reduce the class imbalance and eliminate obvious non-matches from the set of all possible correspondences. And once we do the blocking, we can actually start doing entity matching. Our studies shows that we can categorize these entity matchings in general into two large categories. The first one is rule-based. The second one is learning-based. Rule-based techniques basically define matchers as conjunction or disjunction of a few logical predicates. Each predicate or rule is basically based on some similarity measure, let's say cosine similarity between some attributes, and the comparison operator and some threshold. For example, two entities are a match if their similarity based on some similarity measure is higher than a specific threshold. This kind of rule-based matchers are scalable to very large settings because they're very easy to evaluate, and they are actually explainable because these rules are defined by users. But as you can imagine, they highly depend on human experts. And in order to overcome that, the problem of designing these rules by humans, the learning-based techniques deal with the entity matching problem as a classification problem. And in the first group of these learning-based techniques, we have non-neural matchers. There are many examples of these in the literature. These matchers use a traditional machine learning algorithms such as decision tree or SVM for learning match versus non-match. Overall, these non-neural matchers underperform for unstructured and text data, so they cannot adapt to the free format text. And with the emerging of large language models, now we have many more modern matchers called neural matchers that basically fine-tune these large language models for the entity matching task, and they are perform superior to non-neural matchers for textual and dirty data. So in a fairness-sensitive setting, entities are accompanied with some sensitive attributes. For example, in the case of authors, we have country of origin as our sensitive attribute, and we want to evaluate the performance of these matchers with respect to that defined sensitive attribute. And because we are dealing with some classification task, special case of classification task, when we create these correspondences, we're not only dealing with one group, we're actually could deal with pairs of groups. For example, what I want to evaluate is what's the performance or fairness of my model when I match authors from the same country, for example, from Germany to Germany, or when I match Chinese or American authors. So, of course, for the correctness phase, for the correctness evaluation, we can use typical F1 measure. The more for fairness, the most commonly used type of fairness in this setting is the subgroup and group fairness. And the goal here is to verify whether the matcher has similar performance on different groups or defined subgroups. So the groups can be defined based on just a single type of the single side of the groups. For example, just matching American authors, or it can be based on pairwise matching German authors to German authors. And there are different fairness measures that can be considered, but not all of them can be applied in this task of entity matching, or not all of them make sense. And we need to choose appropriate fairness measures for this entity matching. So one way is to choose fairness measure based on the importance of false positives, false negatives, and true positive and true negatives in the problem context. For example, statistical parity may not be reasonable because it requires equal match ratios for different groups, independent of whether they are the correspondence itself is a match or not. On the other hand, true positive rate parity is useful when correctly predicting the matches is crucial, and false matches do not cost much. And overall, our observation says that certain groups of fairness, such as measures such as positive predictive value parity and true positive predictive rate parity, make sense because these are the ones that focus on successfully discovering very rare matches, which is the case we deal with in entity matching. We have very few matches, and most of our correspondences are non-match. And I think with that, we're going to end the tutorial. More ideas on the future work can be found in the slides.